Welcome back to the deep dive. I want you to imagine something for a second. You're at 38,000 feet. It is pitch black outside.
Total void.
Exactly. There are no landmarks, no highways, no street signs. You have 300 passengers sitting behind you, and they are all trusting you with their lives. And you need to tell a very powerful computer exactly where on this planet you are.
And not just roughly over the Atlantic?
No, not at all. You need absolute mathematical certainty.
That's the scenario that might sound like a nightmare to some, but for a pilot, that's just a Tuesday.
It really is. And that's what we're talking about today. For most people, navigation is, well, it's just opening Google Maps on their phone, right?
Mm-hmm.
But for a pilot, and especially for you, the student preparing for your airline transport pilot license, your ATPL navigation is a language. It's about speaking the mathematical language of the planet itself.
It's the absolute bedrock of general navigation. If you can't speak that language, if you don't fundamentally understand the grid system, you're effectively lost before you even release the parking brake.
And the stakes in the exam are just as high. So we aren't just here to have a casual chat about geography. We are on a mission with this deep dive.
We are.
We are here to crack the code of the ATPL syllabus on direction, latitude, and longitude. We've pulled together information from the big, authoritative navigation manuals, from ATPL theory texts, basically all the core sources.
And my job here, as I see it, is to help you distinguish between what's just, nice to know trivia and what is absolute must know for the exams.
The exam facts.
The exam facts. Because the ATPL exam, it's not going to ask you which way is north. It's going to give you a scenario with exceptions, with historical quirks and mathematical traps, and ask you to apply logic.
I love that. So let's find that logic. Let's unpack the dense terminology and help you get those answers right.
Okay.
Where do we start? We have to start with the canvas we're painting on, the Earth itself.
The best place to start.
Okay, section 1, the shape of the Earth. Now, if I go out on the street and ask a random person what shape the Earth is, they'll say it's a sphere, unless they're a conspiracy theorist, which we won't go there.
Yeah.
But for an ATPL student, just saying sphere isn't quite the right answer, is it?
It's not the full answer, no. Technically, and for the exam, the Earth is an oblate spheroid.
An oblate spheroid. It sounds like a bit of an insult, doesn't it? You oblate spheroid.
It does a bit, yeah.
But let's break that term down. What does it actually mean physically?
To put it simply, it means it's a sphere that's been squashed. Imagine a slightly soft ball that someone is sitting on, just gently. It's flattened at the poles and it bulges out at the equator.
Right. And why? What did the squashing?
Physics did. You have to go all the way back to when the Earth was forming. It was this, spinning cloud of gas and dust that eventually became molten rock.
Okay, so a giant spinning ball of lava.
Pretty much. And because it was spinning, it experienced centrifugal force.
The same force that pushes you to the side of the car when you take a corner too fast.
Exactly that force. Now think about that spinning ball. Where is the surface moving the fastest?
At the equator, the widest part.
Right. The poles are barely moving, relatively speaking, but the equator is moving at over 1,000 miles an hour. So that outward force, that centrifugal force, is strongest at the equator. It literally pushes the middle of the Earth out, causing this bulge.
Okay, so we've got a squashed ball. But how squashed are we talking? Is it really obvious, like a pancake?
Oh, no, not at all. It's incredibly subtle. The term we use is compression, and this is a number you absolutely have to know for the exam.
Okay, I'm ready.
The compression ratio is approximately 1 divided by 300, or, if you prefer, 0.3%.
1 over 300. So if I were looking at the Earth from the moon, I wouldn't actually be able to see the squash.
No way. To the naked eye, it looks like a perfect sphere. But when you translate that ratio into hard distances, that 1,300 really starts to matter.
How so?
Because of that compression, the polar diameter, that's the distance from the North Pole straight through the center to the South Pole, is shorter than the equatorial diameter.
Okay, shorter by how much? This sounds like an exam question.
This is a classic exam question.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best